Moving on now to some of our AP style questions for this homework assignment. So we have our classic experiment conceptual question about the rock and the feather. And so if a rock and a feather are dropped at the same time near the surface of Earth, which one lands first? In the absence of air resistance, they would accelerate downwards and land at the same time, but on Earth we do have air resistance. So why will the rock land before the feather? The first one, the rock does have more mass. That is most likely true unless it's a really heavy feather, but that does not mean that gravity pulls it more. So question A, or response A, is going to be out. Gravity pulls both objects down at the same rate. The rock lands before because air resistance had a bigger impact on the feather. That one is absolutely true, but let's double check the other two. The rock lands before because the rock starts falling immediately and the feather does not start falling immediately. That is not true. They both start falling immediately due to gravity. And then the last one, the rock will not land before the feather. They will land at the same time. Well, if we account for air resistance, then that is not the case. In a vacuum, though, that would be true. All right, moving on here to our next one. An object is thrown straight up in the air and caught at the same height from which it was thrown. We're going to ignore air resistance. We want to know what will be true for the object. So first one, our velocity is 0 at the peak. That is absolutely true. This is one of the ones, though, where we have to select more than one correct answer. So I'm just going to put a check next to that one. Acceleration of the object at the peak is 0. We know that it's 9.8 no matter what. The object will take less time to fall than to rise because velocity and acceleration are the same direction. That is also not true. It's a symmetrical launch. And then D, the time it takes the object to rise equals the time it takes to fall. So that one is also true. So the answers are A and D. Both of those statements are correct. Moving on to 8 here, it says that in the absence of air friction, objects drop near the surface accelerate at a constant rate, 9.8 meters per second squared. So what does that actually mean? This first one, the speed increases about 9.8 during each second. That one is absolutely true, and that does end up happening to be our right answer, but let's work through the other ones. The speed as the object falls is 9.8 meters per second. That is not necessarily true, but there may be a point in time when that happens. The object falls 9.8 meters during each second. That one's also not true. That would imply that the velocity was 9.8, not the acceleration. The object falls 9.8 meters during the first second only. That's the same idea. 9.8 is the acceleration, not the velocity. Completely separate topics. And the rate of change of displacement with respect to time for an object. That really is another way of saying velocity. And once again, the velocity is not necessarily 9.8. That is the acceleration due to gravity, but will not be the velocity for an object in free fall. All right, moving on to the next one, we have this problem here involving a red-bearded tuba player, not exactly sure who that could be talking about, running down the sidelines of a football field who eventually gets chased by a detective, like maybe Sherlock Holmes or something, and eventually caught. And so we want to go ahead and start analyzing this situation. The first thing I'm going to do is I'm going to create a setup for each object. Okay, we have 2 objects, so I'm going to make 2 setups. So for the tuba player, we know the tuba player is running at a constant speed of 12 meters per second, which means both the initial and final velocities of the tuba player will be the same. We also know the tuba player's acceleration is 0 meters per second squared. For the detective, okay, we know the detective starts at rest and accelerates at 3.4 meters per second squared. Now, 2 other things we know that maybe aren't apparently obvious. So we don't have any more numbers, but we can think of some connections that we have between the 2 sides. So first of all, we know that the detective starts running when the tuba player passes. So initially they're at the same location. And this problem ends when the detective catches the tuba player. So that means they run the same distance and therefore have the same displacement. So I'm just going to call that x and x. I don't know what either one is, but I do know that they are the same. I'm also going to call the times the same thing because for however long the tuba player is running, the detective is also running. So those 2 times also have the same value, even though I don't know what that value is. Now that I have this set up, I'm going to write an equation for each one. For the tuba player, I have 0 acceleration, so that means I have to use one of my delta x equations. I'll just go ahead and use this one. And so I have x is equal to 12t plus 1/2 times 0 times t squared. So that second term there just goes away, and I'm just left with x equals 12t. For the detective, I don't know anything about the final velocity, so I'm going to use the equation that doesn't include that, which happens to be the same one, vit plus 1/2 at squared. And so I'm going to say x is equal to 0t plus 1/2 times 3.4 times t squared. So that means when I simplify it and that goes away, x is simply 1.7 t squared. Now that I have those two equations, I can go ahead and think about simplifying those equations, or setting them equal to each other. So they're both equal to x. I'm just going to set them equal to each other, and we have 12t equals 1.7 t squared. Okay. I can divide out that t. I will talk about what that means in a second, because there is an important point there, but we end up with 12t equals 1, or 12 equals 1.7t. So our time here ends up being 7.06 seconds. Now, when I divided out that t, that actually did eliminate a possible solution. The way I can get that solution is to bring both terms to the same side and set it equal to 0. So what I'm left with there is t times 1.7t minus 12 equals 0. We have two things that are multiplied together and they're equal to 0, and that means that one of them must be equal to 0. That's the only way you can have them equal to 0. This is called the zero product property. So either 12 minus t is equal to 0, which is the solution we found here, or t itself is equal to 0. And that makes sense, okay? That's not the solution we want. A lot of times we refer to this as the trivial solution, but that is a solution that makes sense. When are their positions the same? Their positions are the same in the very beginning after neither one has traveled for any period of time. We don't want that solution. That's not the one we're looking for, but that one does work. All right, moving on to part B. Here is our answer for part A. We're now looking for the distance traveled, so we can use either one of our equations, the 12t or the 1.7t squared. I'll just use our 12t. And we're simply going to plug in that time that we just got from part A, and we find that that distance ends up being 84.7 meters. Moving on to C, we have two graphs to draw here, the position versus time and velocity versus time graphs. So I'm going to start with my position versus time. My tuba player is running at a constant speed, so that's going to be the red line. So it's just going to be a straight line with a positive slope. And I'm going to start it at the origin, although you don't necessarily have to start it at that point. For the detective, all right, we're also going to start at the origin, but that's going to show speeding up with a positive velocity. So initially he's not moving, and we're going to be speeding up, and eventually intersecting again with that line for the tuba player. On the velocity versus time graph, the tuba player is going to be a horizontal line showing a constant positive velocity, and the detective is going to be an upward sloping line, all right, something like that. All right, moving on to part D here, we have a few questions about those graphs. What does the intersection mean on the position versus time graph? Well, that means the two objects are at the same location. Okay, if their position versus time graphs intersect, it means that they're at the same position at the same time. What does the intersection mean on the velocity versus time graph? That means they're traveling at the same velocity, okay, or same speed. And then 3, do those intersection points happen at the same time? No. The intersection on the velocity versus time graph happens first. We can see that from the graph I drew, because it is drawn relatively to scale, but either way, we can think about the fact that when the two objects are traveling the same speed, the detective is still behind the tuba player. And the reason for that is the detective must be traveling faster than the tuba player to catch up because he initially is behind. Moving on to our final question here. this is going to be a paragraph-length response style question, so we'll talk about that briefly in a little bit. But we have a situation where there's two people standing on top of a roof. Each of them has a rock, and they're going to throw the rocks. All right, one person throws rock A straight down with an initial velocity of v, so it's going in the negative direction initially. And the other throws the rock straight up with that same velocity. So the first thing we want to do is, on the graph, we want to draw the velocity versus time graph for both objects from time t equals 0 to the point when they hit the ground. So I'm going to go ahead and start with that. So first I'm going to draw rock A, which is starting with that negative velocity, and it is going to simply be speeding up as it falls. All right. Rock B is going to start up here with a positive velocity, and initially it's going to slow down, okay, to 0, all right, as it rises to its peak, and then it's going to begin speeding up in the negative direction, so continuing on down like that. Okay, something like that. One thing we should notice is both of these objects are accelerating down at 9.8 meters per second squared. Okay, so the slope of the two lines, and obviously it's not easy to get this perfect, but they should be relatively the same. Okay, in theory they are exactly the same, but obviously it's a little bit difficult to draw that. All right, so it should look something like that. The second part says, in a clear, coherent paragraph-length response, explain which rock will be moving faster when it hits the ground. Feel free to use this graph to provide some support. So we're going to talk a little bit about this question in general. With these types of questions, we want to first make a very strong statement, all right, just answering that question, and then we're going to provide evidence. And usually it's going to be in a very logical format where we state one thing, which leads to another thing, which leads to another thing, ultimately explaining our answer. So I'm going to start with stating what the correct answer is. And the correct answer is the rocks will hit the ground traveling at the same speed. And there are a few ways I can do this. So let's talk through the solution and then we'll write out an answer. So the one thing I can think about is, all right, if I just think about the path of the two rocks, right, the one, rock A, is just going to go from here straight down, and so it's initially traveling at negative v at that spot. Rock B is going to go up to the peak and then go down, and it's initially traveling at v when it leaves the person's hand, but that means that when it returns to that same spot, it's going to be traveling down at a velocity of v. So if I consider the flight of A, that's actually identical to B once B returns to that level from which it was thrown. So that last part of the flight of B is the same as the flight of A. We can also see this on the graph, okay? If we look at it here, we can see that at this point here, the two objects are traveling at the same speed. And what is that point? Well, that's the point where rock B actually has a displacement of 0. This positive area and this negative area should be the same, and I realize I didn't draw that perfectly, but that's the point when it returns to its initial starting position. And we can see that this line here and this line here end up having the exact same look to them, which means that they hit the ground traveling at the same speed. They're identical from here on. We could simply shift this line and put it right here, and it would match up perfectly. So let's think about how we're actually going to go through explaining this. So the first point that I would make is that both objects are accelerating down at the same rate, 9.8 meters per second squared. The second point that I would make is at this point here, which I'm going to actually label as T on my graph, at T, as shown on graph, B has the same velocity as the initial velocity of A. And then I would say that this point is the point when it returns to the location where it was thrown. And you can even mention that the area under the curve is going to be the same at that point. So we can say from that point on, it has the same initial velocity and acceleration as A, so it must hit the ground traveling at the same speed. And there you have your answer. Definitely want to think about making your first point, that's key, and then having a few logically ordered supporting points that lead you to that answer. So there you have it.